Okay, good evening. This is Professor David J. De Los Reyes. Okay, it's August 9 now, and the time is around 12:31 a.m. My discussion for this morning, it's now this morning, it's past 12 o'clock, it's August 9. My topic for this morning will be alternating current circuit, and this will now be lesson number 16. Okay, let's proceed. This is a long video format discussion. Okay. The subject matter for this morning will be alternating current circuit, lesson number 16. Okay, number 16. Example calculation of impedances in parallel, meaning example calculations, okay, when the connection of the impedances are actually in parallel. Okay, let's try to bring out an example problem so we know how to calculate under parallel impedances. Okay. We are given a parallel impedance. I just give 2 for it to be considered parallel. At least the minimum number of impedance for a parallel will be 2. So this is C1 and C2. They are connected in parallel. This is the voltage of the source coming from the utility line. The voltage of the utility line is 120 volts. We assume that we are in the USA. I am here in Los Angeles, so it's actually I'm here in USA. The frequency is 60 Hertz. So this is Z1, Z2. This is I total. This is I1, I2. The given condition of the parameters of the impedances is that Z1 is actually 12 plus G16 ohms. And Z2 is 8 minus G16 ohms. So it seems this is a motor load. And this is a capacitor. Because this is minus and this is plus. The given impedances are actually given in the so-called rectangular form. 12 plus G16, 8 minus G16. The problem is asking, there are so many unknowns, okay? Find capital letter Y with the subscript T, meaning total admittance. Capital letter C with the subscript capital letter T, meaning total impedance. Capital letter A with the subscript capital letter T will be the total current. This is I sub 1, I sub 2. The total true power consumption of the two impedances. Okay, the total reactive power consumed by the two impedances. The total apparent power, okay, consumed by Z1 and Z2, and the power factor of the system. There should be a power factor. Is it efficient or it is not efficient? Okay, let's try to bring out the solution. I will make the discussion to be as concise as possible because the computation is very long. It's not so, what you call this, complicated, but you are just following a concept, and if you know how to follow a concept, the solution should be as simple as possible. Okay, let's try to bring out the solution. Z1 is 12 plus G16. Converting this to polar, this should be 20 angle 53.13 degrees. Use your calculator to convert this 12 plus G16 to polar. 16 divided by 12, press arctangent. What will come out will be 53.13 degrees. Take the cosine. You divide that cosine value to 12. What comes out for the magnitude of the total impedance number 1 will be 20 ohms. The magnitude of the impedance is 20 ohms. And the angle is 53.13 degrees, and this is plus. So it should be inductive, and it is a motor load. Let's try to compute for admittance number 1. The last time around I said that admittance is actually 1 over impedance, right? So if the given circuit is parallel, I think the positive solution on how to compute for the impedance will be to work first on the admittance. So we shall compute first the admittance. Y1 will be 1 over Z1. by following this formula, this should be 1 all over 20 angle 53.13 degrees. The ratio 1 over 20, no. It is here, 1 over 20. The ratio 1 over 20 will be 0.05 and the angle is minus 53.13 degrees. We bring this up, so 0 minus 53.13 is a negative 53.13. The unit is mho. In terms of rectangular, because later on we will be adding y1 and y2, so we will convert this y1 now to rectangular immediately, ASAP. So this is 0.03 minus j 0.04, meaning take the cosine of 53.13 times 0.05, it will be 0.03. In the sine of 53.13, you multiply that to the magnitude 0.05, it will be 0.004. 0.04. It should be negative because the sine of a negative angle is sine, right? So this is minus j 0.04. Converting C2. C2 is actually 8 minus G6, right? Converting to polar, you take the ratio 6 over 8. Press arctangent, what will come out is negative 36.86 degrees. Negative, because this is minus j. Take the cosine of this, you divide that to the value 8, what will come out for the magnitude of C2 will be 10. So we now know C2 in terms of polar. So again, by using this, we could compute for Y2, okay, by using the formula, admittance number 2. The admittance equivalent of this impedance will be 1 over C2. This is 1 over 10 angle negative 36.86 degrees. 1 over 10 will be 0.1. We bring this up, so this should now be 36.86 degrees. Converting this to rectangular. Okay. Take the cosine of 36.86, multiply that by 0.1, it will become 0.08. Take the sine of this. Okay, you multiply that to 0.1, it will be 0.06. So the admittance number to y sub 2 is in rectangular is 0.08 plus j 0.08 mho. So if we try to compute for the total admittance of this, okay, it should be y1 plus y2. This is the rectangular equivalent of y1. This is the rectangular equivalent of y2. Okay, combining similar terms, real to real, imaginary to imaginary. This is real, this is imaginary. What comes out will be 0.11 plus j 0.02. Okay, converting to polar, admittance are actually small values because it is the reciprocal of impedance. So just be very careful, right? 0.02 divided by 0.11, press arctangent, what will come out will be 10.3 degrees. Take the cosine of 10.3, it's almost 0.9 times 0.11, what comes out? Cosine. We divide that to 0.11, what will come out will be 0.1118. Okay, so the magnitude of the total admittance of C1 and C2 is actually 0.118. And again, by using the definition, impedance is actually y over y total. We now know y total, right? So to compute for the equivalent C total of this, okay, it should be 1 over y total. Because we converted first this one to admittance, then we will take again the reciprocals. Okay, so we could solve immediately for the equivalent of these two here if they are connected and parallel, right? So C total now of the given two impedances will be 1 over y total. 1 over 0.118 angle 10.3. 1 divided by 0.118 will be 8.944. We bring this up, so this should be negative 10.3 degrees. Okay, ohms. The unit is ohms. Okay, so the magnitude of the total impedance, the equivalent of this is 8.944 angle negative 10.3. The angle is negative, so the capacitive portion is actually more powerful than the inductive because this is negative. And converting this to rectangular, take the cosine of this, multiplied by 8.944, that will be 8.8. Take the sine of 10.3, you multiply that for 89944, but it should be negative because the sine of negative 10.3 will be negative j1.6. It's downward. Right? So the rectangular equivalent is 8.8 minus G 8.6, meaning the single equivalent of this is actually with the value 8.8 minus J 1.6. That's the overall. Okay? So this portion is the resistance and this is the capacitive reactance. Or that's the single equivalent. Okay? Let's try to compute for I total. We now know the single equivalent of this. So the total current will be the applied voltage divided by the single equivalent of the impedance. It is 120 over 0 degrees. We make this one as 0 degree. It's a reference vector, right? So 120 angle 0 degrees. The total impedance in terms of polar is 8.944 angle negative 10.3. We are dividing two polar numbers, right? So 120 over 8.944 will be 13.416, and the resulting angle of the total current will be 0. We bring this up, it will now be plus, angle 10.3 degrees amperes. So the magnitude of the total current here, this is 13.416 amperes. Okay, the magnitude. Okay, I will try to erase this one because I want to show the current. Okay, so we now know the magnitude of the total current around 13.416 amperes. That's the total current. If we try to compute for I1, it's an easy matter now. It will be E over C1 because the voltage here is same as here, same as here. We know the polar equivalent of this, so we could compute for I1. That will be E over C1. 120 over 0 over 20 angle 53.30 degrees. It is this value here. What comes out will be 120 over 20 will be 6. The magnitude is 6. We bring this up. It is negative 53.13 degrees amperes. That's the total current here. It is 6 amperes going down. Angle minus 53.13 degrees. It's a complex current, right? Converting this one, it will be 3.6 minus J 3.8. Take the cosine, multiply by 6, that will be 3.6. Take the sine, multiply by 6, that will be 4.8, but it should be negative. This is negative, right? Let's try to compute for I2. I2 will be, the voltage across C2 is still E, equal to the applied voltage, right? 120 angle 0 over 10 angle negative 36.86 degrees. 120 over 10 will be 12. We bring this up, so this should be 36.86 degrees amperes. So the current here is actually 12 angle 36.86 degrees. This is a lagging current, negative. This is a leading current, this is plus, right? So this is 6 and 12. But you cannot just add 6 and 12 to be equal to 13. You should add it vectorially. Because this got a real part, imaginary part, real part, imaginary part. Use the triangle method, right? Okay, you use the vectorial addition. So, I2 now, we convert this one to rectangular, 9.6 cosine times 12 will be 9.6, sine times 12, that will be 7.2 amperes. Why did I get the value of I1 and I2 in rectangular? Okay, because I want to check the validity of the total current. Let's try to check the value of the total current if it is really the sum of I1 and I2. Because from here, obviously, I total will be I1 and I2, right? So I total, as you check, this is not a part of the solution. This is just a checking method, right? Let's see if the solution is worth checking it, right? I total will be I1 plus I2. I1 is actually this one. I2 will be this one in rectangular. We combine similar terms, real, real, imaginary, imaginary. So this should become 13.2 plus G2.4. Okay, let's try to convert this rectangular to its polar form and let us see if the total current is really 13.416 amperes. You divide 2.4 by 13.2. What will come out will be 10.3 degrees, right? Take the cosine at 10.3, you divide that to 13.2. What will come out will be 13.416. And this 13.416 is actually same as this one. Right? They are the same. So by bringing out two solutions, okay, I total by the direct solution is 13.416, and by taking the sum of I1 and I2, what comes out still for the value of I total is 13.416. The angle is 10.3 degrees ampere. 10.3. The angle here is plus, meaning this is a leading current. The power factor is leading. This is the applied voltage, and this is the current, and the angle between them is 10.3 degrees. So if you got the graph, if this should be the voltage, the current lags behind the applied voltage by 10.3 degrees, so it could be this one maybe. The angle of lag is 10.3 degrees, this one. Right? That's the meaning of this. Okay, the last part of the solution, it's an easy solution now. True power will be the total current times R total. We know the magnitude of the total current, 13.416 square. The total impedance in terms of rectangular is actually, where is the value? It is this one, 8.8 and 1.6. The absolute value of total resistance, the single equivalent of these two, is 8 ohms. The inductive portion is actually 1.6, and the total impedance is 8.944. Where is it? This is one. So true power, square of the current times R, 1583.90 watts. Okay, it is this portion. Q total will be the square of total current times X total. X total is the resulting net X portion, inductance portion, it's only 1.6 ohms. So this is 13.416 square times 1.6. It's very small already. 287.98 bars. Reactive volt ampere, right? So reactive volt ampere. S total will be the square of the current times C total, 13.416. C total is actually 8.944. Okay, the total value will be 1609.82 volt ampere. The product of voltage and current, that is volt ampere. So it is this portion here. It is a right triangle. Okay, and for the power factor, by definition, power factor is the ratio of true power over the apparent power. Okay, it will be 1583.90 divided by 1609 times 100%. It is 98.39%. Or another solution for the power factor, take the cosine of this angle here. Cosine of 10.3 is 98.9839 times 100%. So it is still 98.39% as it checked to the value of the power factor. Okay, that's it, guys. That's the way how to compute total admittance, total impedance, total current, I1, I2, true power, reactive power, apparent power, and power factor if the given circuit is parallel. Okay? Okay? Okay, so for those of you who are taking up or who are supposed to take up electrical engineering, this is for you guys. This is the heart and soul of alternating current circuit calculation. The foundation is actually complex number, okay? Complex number, that's coming from algebra, okay? So if you want to subscribe to my channel is at youtube.com/@prof.davidj.de. If you want to share it, please click share. Okay. Try to watch my long video format discussion on alternating current circuit. I am assuring you, you will get something from it. Okay, good morning from Los Angeles. Professor David J. De Los Reyes.